Welcome back to lecture 12, and let's continue talking about the penalty parameter or the barrier parameters of mu k. How do we update that? The penalty parameters, mu k, we're trying to do is when k goes on increasing, mu k will be approaching to 0. Therefore, we make sure the problem p mu is converged eventually to p1. So what we do is we're using a mu k equals to sigma times the phi average k, which is the phi average, what we call it is the average duality gap. So that's what we usually using this. So we basically update mu k as a part of the average duality gap. So we know that vk is also less than or equal to 0 in that case. And next we'll talk about the step length. Okay, after we construct the scheme to update the penalty term or barrier parameter, the step length beta k can be we know that actually sk times dxk times capital Xk times dsk equals to vk. And the vk, by definition, equals to mu k times e minus capital Xk times capital Sk times e. So therefore, for each terms in capital X and capital S equal to Sik times dsik, okay, plus Sik times dxik equals to the mu minus Sik minus Sik, in that case, equals to mu k minus phi ik. So if we put it into a matrix format, looks like this. Capital Sk times dxk plus capital Xk times dsk, okay, equals to mu k, which is mu k times e all the way here, minus Sik times Sik. So this is pretty much what we have in this case. Okay, let's take a look at the step length beta k. How is that going to work? Okay, first we look at the new complementary slackness condition. We call the phi ik based on the beta step size, and equals to xik, which is the current primal solution, plus a beta step size times dxik, which is the direction. Also, same thing, update the new slack variable, do slack variable sik plus current sik plus a beta step size times a dsik. After we multiply these two terms together, we have first xik times sik. And the second terms only have a beta times sik times dsik, or sik times dxik times beta. And then we have the quadratic term, beta squared times dxik times dsik. And this is the term we have. So we're going to use this to find out what is the best step size beta. Since we know, okay, the dsik is the direction of the primal variable, and the direction of the do slack times together equals to 0. And we can calculate the new average duality gap based on the current step beta equals to sum of the phi ik based on the beta equal to this. Once we multiply these two out, and actually because primal direction times do slack direction equal to 0, so the quadratic term disappear right here. So we end up with 1 minus beta times the previous average, okay, previous average, plus beta times mu k. And the mu k equals to sigma times this average as well. We talked about it before here. Okay, mu k equals to sigma times the duality, average duality gap. So this is fairly straightforward. We have. And now we define another variable measurements called C. Okay, the psi actually, and psi of beta equals to the minimum duality gap plus beta times tau times the average duality gap minus the minimum duality gap. Therefore, it is similar to the previous one, equals to 1 minus beta times the minimum duality gap times beta times tau times the average duality gap. And tau is between sigma and 0. Once again, sigma is used to define the mu k equals to sigma times the average duality gap. So this looks a little bit complicated, but the development of these actually guarantee the global convergences of Primal-Dual Affine scaling method. We'll show you later on, actually, we can implement this much easier, but this is the theoretical development. Let's look at that next. If for each one of the elements inside the dk transpose times dsk, which is these dk transpose times dsk supposed to be equal to 0, but each one of the element within may not be 0. So if some of them are non-negative or positive, so the new duality gap will be greater than this psi k, okay? But if the dk dxi k times dsi k, which is the sum of the element in dk times dsk, are less than 0, then we have a two situation, okay? The two situation, one is if for beta between a certain level of gamma equal to this, okay, from 0 to beta equal from 0 to gamma, and the new duality gap will be greater than the phi function, phi measurement. And if the beta is greater than gamma to 1, then the new duality gap for this particular variable will be less than or equal to the phi measurement. The measurement is, we just simply define the previous slide. And we can also figure out a maxima value. We'll only look at these two situations to determine a bound called alpha k, which is a maxima for these two to satisfy. And therefore, the step length for case iteration can be defined easily. Either as 1, maxima is 1, and or if alpha k is less than 1. So we define minima of those two. For practical implementation, we can use as before. We simply say alpha k equals to 0.95 or 0.99 of 1 over k. K is the number of iteration. So we guarantee the alpha k started with 0.95 or 0.99 and gradually increase close to 1. I'm sorry. Look at the, now we review the entire Primal-Dual Affine scaling algorithm to summarize everything together. Initialization, we set the iteration number to 0 to begin with, and find the initial feasible solution. And this is not really necessary in a primal and dual affine scaling method. But if it's they are all primal and dual feasible, and this is easier for convergences. Also, we're going to set as convergence tolerance epsilon is greater than 0, a small real value. Usually is epsilon can be set to 10 to minus 6 or 10 to minus 3, depends on how close you want to be a corner point. Then we let sigma and tau to be control parameter, and tau is less than sigma, and both of them is between 0 and 1. And hopefully is slightly less than 1. And we're going to calculate our duality gap, Sk transpose times Sk. If this value, which is our duality gap, or complementary slackness, as defined, is less than the epsilon, we call the current solution is optimal. Otherwise, we'll go to the next step. The next step is calculating the average duality gap and the minimum duality gap. And we set the barrier parameter or penalty parameter mu k equals to sigma times average duality gap. And calculate V, Vk equals to mu k times E minus capital Sk and times capital Sk times E. So this is, well, hopefully the Vk currently is not 0. Eventually it's going to converge to 0, but this term will be equal to that term. Since initially, if we have a feasible solution, primal and dual feasible solution, and the direction can be calculated in a simplified form without even involve Tk and Uk we're talking about. And Tk is the primal infeasibility, as we defined it before, and the Uk is the dual infeasibility. If a primal current solution is primal feasible and dual feasible as well. So this is a simplified version to calculate d omega k, then dsk based on the d omega k. Then the dxk can be used to calculate based on the dsk. So calculate the improving feasible solution. Step number 4 is determining the step size. Like we said before, we calculate calculate an alpha k as upper bound for the step size. And this upper bound can be either 1 or whatever alpha k is. So we don't want them to be greater than 1. As we said before, we can just set beta k equals to 0.95 to the power 1 over k. Okay, like a primal and dual affine scaling method as well. Then finally, we update our primal solution, dual solution, and the dual slack, and update my iteration number, and go back to step 2 to check optimality. Okay, this is the only complication we have in this portion is the step size beta k, and involves certain measurements in order to mathematically prove their global convergence. But the practical implementation will be can be much more simplified without going through all these. Okay. In fact, we're going to present you a numerical example and Excel example, and to show you how can we easily implement this primal and dual, also referring as a so-called path following algorithm using a Microsoft Excel. So to sum it up, this algorithm is intentionally trying to start with a primal feasible solution and also a dual feasible solution, and in order to reach the optimal, it's trying to achieve the complementary slackness condition. Okay, and primal affine scaling method or regular simplex method is trying to maintain the primal feasibility, and throughout the simplex tableau or throughout the primal affine scaling algorithm, they're trying to maintain the complementary slackness condition as well. So they always calculate the dual solution based on the current primal solution. And dual affine scaling method is trying to maintain a dual, start with a dual feasible solution and maintain the complementary slackness by calculating primal solution based on the current dual solution. Okay, until it reaches the primal feasibility, then you have the optimal solution. Again, the KKT conditions are 3 parts for linear programming, for nonlinear programming as well, meaning primal feasibility, dual feasibility, and complementary slackness. This path-following method, the Primal-Dual Affine scaling method, is maintain a primal feasibility and the dual feasibility in the beginning, and trying to reach complementary slackness, and in the end to reach optimal. So each one of the method start with a certain condition and trying to reach the other condition. So this is a fairly summarize all this algorithm we introduced so far. In the next few lecture, I'm going to go over the numerical example for each one of the algorithm and present you some computational insight as well. So we'll see you in the next lecture. Thank you.